let's say, image recognition, image classification, models. They go very deep, they do kinds of other things, but this is the basic idea that we're going to be doing. Essentially, you look at a small window of your image, you compute some little function on that, then you move the window a little bit, compute the same function, just on slightly different pixels, moved over one, say. And you'll compute a bunch of little outputs, and it's like you're making a new little image from all these little tiny glimpses into your image. This is a way to find, like, I don't know, all the edges, all the things look like L's, all the things look like other stuff. Whatever. Whatever you're going to do. Anyway, I've already read in my data, so we're good to go on that. We should be good to go in general. Are we streaming? We are streaming. Should be okay. Should kick on in a second here. I might have to reboot my page. Yes, so that's what we're going to do. I've already read in a lot of this information. Here's our current dopey model, which is fine. There's nothing inherently wrong with it. But we're going to make a number of changes. So you see here we start off with this dense and this input shape business. This, like, 28 by 28, whatever. That's got to get changed. Because going back up to the top here, we instead are going to be using this conv2d thing. That's this convolution 2D. Let's take a look at that, just so you know what you're looking at. 2D convolution layer, ed, spatial convolution over images. That's kind of what we're going to be doing. The filters, the number of things we're going to be computing, I think. Hang on. Dimensionality of the output space. No. This is the window size, right? Number of output filters? No. This is, the number of things we're computing for each window that we're looking at. Kernel size is how big is the window. So that could be a different size in X and Y. Almost always people use the same X, Y size because you're dealing with some actual spatial thing. So it's relevant to say, well, I want to look at squares. I don't really want to look at rectangles. There are insano universes where you don't want to look at rectangles either. You want to look at arbitrary shapes. But that's not the universe we're living in right now. So we're going to skip over all these wacky loss functions that we didn't like. I'm going to comment out this, and we're going to make a new line, model.add. It's going to be conv2d, hang on. And how many input filters do we want, right? Well, let's just say, I like power to 2, let's do it 8. Compute 8 things. Let's do too many. Let's do 4, right? Kernel size. Let's say a 3 by 3 window, right? I can just pass in an integer or a tuple, specifying the kernel size. Cool. So you'll look at little 3 by 3 windows, and in each little window, you'll compute 4 different things. Those 4 things don't have a spatial representation, it's just 4 different things. Like you can imagine, like, let me count up all the green colors, let me count up all the reds, let me count up all the blues, and let me count up the square of the blues. Those might be 4 things you can compute. And that represents sort of the center of whatever that window is. Then you move the window over, so you get new values in all your pixels. Great. Kernel size. Strides, this argument here, this is how much you move your window by. Padding is what kind of output shape do I want to end up with. So this window is like 3 by 3. You know, it's going to help for me to load up a GIMP here. I'm just having a feeling that's going to make it a little clearer. I know I described convolutional neural networks on this channel before, but, it can get really complicated. And not everyone has seen that. How big is this? Oh, make a new thing. I don't care. Yeah, sure, whatever. Size, make this much more smaller. Right, okay. So, you've got your whole big image. Imagine this whole, this is our image, right? But you might have a little window of it. And, maybe it's just a 2 by 2 thing even that you're looking at. These are all different pixels, and you're going to compute a bunch of different outputs. You'll have output 1 over here, another output, that's something else, and maybe just stick with 2 for now. But they're all going to be functions of all 4 of these pixels. Go back to the red here. All 4 pixels, right, is going to be computing those values. You compute that based on some weights that your model's going to learn, whatever. And then you take this whole dang thing and you're going to shift it over a little bit. Except I didn't actually grab anything because reasons. Can I not actually? There we go. you're going to take the whole thing and, you know, shift it over. How much do you shift it over? That's the stride. So if you say 1, 1, you'll say, okay, well, I want to shift it over 1 pixel to the right, and when I get to the end of the line, I want to shift it down 1 pixel. The next argument that we saw was that padding, which says, what do we do when we're on the edge? Do I want this thing to only be on the edge where I have actual values? Or am I willing to move it partially off the edge? So if you say padding equals valid, you'll go right up to the edge on this side, and right up to the edge on this side. Note that they'll line up. So you'll end up with something smaller in the end. If you say padding equals same, you will go out enough, do enough partial overlap, such that you will end up with the same size object at the end. So that's the idea. If you're doing something fully convolutional, you're probably going to use padding same, or you have some spatial reason to keep that data around. For image classification, yeah, generally we don't worry about it, because I'm going to be grinding all this down to something else anyway, so who cares, right? So we'll do padding equals valid, so we're not adding in any extra non-information. Typically when people pad, you pad with zeros or do something else if there's some intelligent thing to do. If the left side of your image, get another color here. If the left side, for whatever reason, happens to, why not? Oh. Edit, select none. All, whatever. Oh, come on, man. Oh, there we go. No, background. If the left side, my GIMP is broken. All right, whatever. If the left side happens to wrap around to the right, there's ways to pad that way, similarly top and bottom, so that's not actually a square, that's some kind of, you know, surface. There's things you can do. I'm gonna kill this because GIMP is being silly. Discard. No, I don't want it. Anyway, those are the kinds of things you can do. We're not gonna worry about that too much. Point being, strides 1, totally fine. Padding valid, totally fine. I'm not going to worry about data format, dilation rate. This is like where are the inputs versus the spatial dimensions. I think spatial last is the default. Let's find out. Data format, channels last is the default. In Theano, it was different from TensorFlow. Channels first was the default. Caused all kinds of problems for people. I kind of liked it that way, but that's me. I have no idea what dilation rate is. I want to find out. Integer terms of specified dilation are used for dilated convolution. Cute. Okay, so that doesn't tell you what it is. And activation. You can put an activation after it, or if it's a built-in one, you can just say, hey, do the activation here. We're just going to do it here. Make our lives a little simpler. And we're not going to worry about regularization right now. That will be something we consider in the future, though. So, I didn't need to worry about padding. I didn't need to worry about strides. Those were all fine. Activation equals, we're going to do rectified linear. It's very common used in convolutional models like this. So we're going to do that convolution, but in the end, I still want to have 10 numbers. That's always the catch here. So in fact, so if you said, well, I'll just compute 10 things for every pixel, because, well, not almost every pixel. In fact, yeah, no, for almost every pixel, because we're doing padding equals valid. So we're going to get a slightly smaller image, right, with our kernel size 3. The inputs are 28 by 28. We're going to get 26 by 26 out, right? We're going to lose some pixels. That's okay. Cont2D, we probably need to put it in. Do I need input? Is that a thing I have? Whoa. Might need a specific input layer. Maybe I can just do it here. Does Cont2D have input shape? Let's find out. Can it act just like the dense layer can? Doesn't look like it can. All this other nonsense. Input shape, yes. Okay, it can work the same way. Fine. That's good, that's good. Let us then actually do this. We'll say input shape equals 28, comma 28. I think that's good. I don't know, we might need to say 1 here. We might be able to get away without doing that. We're going to find out. Okay. This will compute a bunch of things. This is going to be 10 spots in every pixel. That's way too many. I don't want that. So we'll do this. Then we need to have our proper output. At the end, we need to have something like this. Right? We need to compute 10 numbers in the end. There's a problem though. If you say dense, that's expecting an input that's like a one-dimensional list of values. This is not one-dimensional. This is, well, literally it's like three-dimensional because you got the spatial dimension and you got two outputs here. So what you can do, one thing you can do, is add what's called a flattening layer. Did I import flatten? Probably not. I did. Oh, what do you know? Flattens the input. Does not affect the batch size. Right. Oh no. There we go. Scroll up a bit here. Data format. You don't. It doesn't really take any arguments. Essentially, you don't have to worry about that. It's yes. The channels are last. That's fine. So we'll just say flatten. What this does is it unrolls your big 2D mess into a big one-dimensional thing so that you can compute things like this on it. So this is super common in a convolutional kind of world. So what have we actually done here? We have actually computed some interesting features that are like real local, rather than these little features depending on every single pixel. They just depend on parts of pixels, and then we're going to compute like outputs on each one. So this initial thing here, this is like computing some little localized features, little localized filters, and then you're just doing essentially a linear model again, like a logistic regression for each possible digit as well, though. So that's all we're going to do. That's all a convolutional network inherently is. We're going to go over some slightly more complex things when we get there. Let's see how this goes. Whoa, wasn't happy. What was it not happy about? Input 0 of layer count is incompatible with layer expected. Oh, right. There's a couple problems here. Couple problems. I don't think I want to reshape this. What is this? Yeah, I don't want to reshape anything anymore. The shape is now correct because it is two-dimensional. There we go. Was that correct? Yeah, there we go. Take care of that. Perfect. Let's investigate this error a little bit more, though. This is I'm trying to do our convolution. Input 0 of layer count is incompatible with the layer. Expected number of dimensions 4. Found number of dimensions equals 3. Full shape received. None 28, 28. Okay, so you do have to say that there's one input channel. In fact, let me fix this. So we have to reshape a little bit. There's one input channel. If you're doing like color images, red, green, blue, you'd have 3 here. But we have black and white, so it's just 1. So what do we want here? I want 28, 28,1. There's other ways. I'm sure we could fuss with this, just expand the dimensions. TensorFlow has some built-in ways for handling that, but it's easy enough for us to just do it right here. All right, let's try that. Let's just try to add this bit and see if that goes okay. All right, and I didn't turn off my auto indent. It didn't burn me yet. All right, flatten, add another one of this, and let's compile it. Cool. Let's take a look at model.summary. You're going to see something. Yes, output shape, 26, 26. Remember, the input shape is 28, 28. 1, 26, 26, 2, because we did that valid padding. So we lost some size. So we have 20 parameters we're learning in total, which is 9 for each of 3 by 3 window. So that's 18 total, plus 2 bias terms for each of these outputs. Then we're going to take all of this nonsense, this 26 by 26 times 2, yeah, all 1352 of those, flatten them all out, and compute 10 numbers. And so we need all of these times 10, right, plus 10 more equals this number. The 10 more being the 10 bias terms for each of these outputs. So this model has a lot more parameters than we had before, doesn't it? Maybe not, actually. Before it was 784 times 10 plus 10. You know, so it's got almost twice as many parameters as the super dumb model. But if we did 784 and I was computing 10 things, right? So I need this many, yeah. What if I had that for my first layer, and then each one of those gives me 10 things for the next layer? You know, that model might be actually bigger. Whatever. We have a model now. We can use it. We can do some stuff. We can run training. You're gonna notice it's taking a lot longer than before. You're running this little filter over everything, There's just a lot of computations, but it's still cheaper than if you had a fully connected network and I was computing not two things for every window, but two things based. If I was computing two things 784 times, but using these 784 inputs a little bit differently every time, it's an equivalent to that kind of thing. The accuracy metrics for which this is, now keep in mind this accuracy is counting your zeros being 0, which most of them are. So like your random accuracy is about 80%. So validation accuracy, not good. Ability for the model to just memorize information, pretty good. We're not even gonna let this finish here. I'm gonna change this to like 2. Maybe this model could eventually learn something, but oh no, I'm wondering what was. Actually, I'm curious now. I was loading a model earlier. Validation accuracy. Oh, 0.8. So I was getting like 88, 89, 88 or 90 validation accuracy before. What am I getting now? I thought maybe I'm misreading that. Oh no, the validation accuracy is 0.9. So it's about the same. Maybe this model isn't hard enough? I don't know. That's like half the time we can get 2 correct, right? So that's not that good, really, all told. But it is what it is, so you try. 12. Why did this take 20 seconds? All our C's are 12, this one was 20. It took twice as long, almost, for every sample. That's super strange. I wonder if like something in the streaming slowed it down a little bit. Anyway, this model really isn't climbing anymore. Even the training accuracy is not improving. Of course, we have no regularization or anything. The validation loss has gotten worse, right? The training accuracy, whatever. We'll let it finish. It's got 5 more seconds. It's the most boring part of the demo. But it's kind of the part that has to be done. You have to train a model. Well, not all models, but machine learning models like this, based on your data, you do have to train in some sense. Here, we check it. Oh, right. I don't want to reshape. I don't want to reshape like that. 28, come on, 28. It's like, maybe I should have just saved it this way. Maybe. That's going to take a little bit of time. These are our predictions now. Let us... Let's print that sheet. Yes, we got all these things. So we can do the usual things. Plot that P color mesh. Pred. We can do this, as usual, for our 10 classes. And of course you got your multitude of different things. I think the yellows are big values, the purples are low values. I'm pretty sure that's the case. So you get some mix of values. It's reasonably interesting. Look at the histogram of the predictions. A lot of them are real small, which makes sense. And then a mix of values and other ranges. Maybe I believe it. Maybe I believe it. There's nothing actually 0, which is interesting. And then this next one is like, 0.1, 0.2, 0.3, yada, so on and so forth. 0.99 is obviously essentially 1. Okay, that is fine. So our nominal, the percent exact matches for all labels in the image. What is the place where we actually get it exactly correct? 35%. Random is 20%. So something. This Jacquard similarity score. Yeah, that's looking pretty decent. When you're just saying 0.5 is my threshold. Okay. You could take the top 0.2 or the top 2. Maybe that would be better. And I no longer think this is the correct thing to do. Like, my predictions are all probabilities. VLab is like yes, no, right? Yeah. So this is not the percent correct. This is just grab the probabilities that are correct. Yeah, and I want to know of those which ones are greater than 0.5. So actually, I need to fix this. Do this. Put some parens around this. We're gonna do some wild stuff here. I want to know. Whoa, wrong way. Of these, what is greater than 0.5? That's my threshold, right? To say that, like, yes, this was actually correct label. And then, that's true, false, whatever. We're going to sum up over those. And then divide by the number of labels we have, divide by 2. Yeah, I think that's fine. Alright, so it turns out to be about the same. Well, fine. Fine. Oh no, what did I do? Wrong window. Oh boy. That's what happens when I paste in the wrong place. That's not what I wanted at all. Okay, that was not fun. Let's just type some stuff. Yeah. Do this. Yeah, there we go. Okay, let me just clean this up myself here. I just wanted to look at this number, this stuff. 1160. What is V image? Yeah, how long is it now? Of course. 8192. Okay, that's actually not terrible. So in 60% of the labelings, this is like our recall, essentially. We are able to find that correct label. But probably there's other times when we found incorrect labels. And so it's not good. That's why you got things like this. Yeah, that's not super good. Okay, but we have this data set now. Now we can make changes to our model. We can try some other things. So you can keep doing more and more convolutions, sort of like you can do more and more layers normally. But that's not always the right thing to do. Do I have? I don't have. There's another kind of layer called a max pool, I think. Layers, max, nope, max pool 2D, that's what we want. Max pooling operation. Okay, let me import that. Max pool 2D. What this layer is going to let us do is take one of those little windows. Let me open GIMP again, because that's fun. Take one of those windows where we've computed some interesting outputs. Who knows, whatever it is, doesn't matter. Yeah, there we go. Oh, one, perfect. You got your big, oh, come on. Oh, what? Oh, it's terrible. I don't want that. Take your big image. Right? Or whatever. Take that big image. You've got this little window of things let me rephrase this. You've computed a bunch of new little things. So you got some new, you got some new things. You've got now like a 26 by 26 thing, right? Because you cut off a pixel on every side. A bunch of little things here. Whatever. What we want to do is take all these computed values and shrink this a little bit, because probably most of these are very similar. They represent the same kind of things. In general, if we want to combine, say, these four things together, there's a couple different ways you can do that. I could say, give me the average of all these and produce one value. Right? We want to produce one value. Or I might say, instead, you know what? Just give me whichever is biggest. The maximum value of these four. And then we'll move over to, we disregard all those pixels. We don't disregard them, we compute this value. And then we make a new value from like these 4 pixels. And we take the maximum again. And then on these 4 pixels. And on these 4 pixels. And so on and so forth. And you end up with this new image that is half as big as this red one. So it'd be like 13 by 13, say. A thing here, and a thing here, and a thing here, and so on and so forth. Get some ellipses there. That's max pooling. If you do the average, that's called average pooling. You can take the minimum or whatever as well. If you can take the minimum, you can take the maximum. It's all minus signs can make your life simple there. Generally, people do max because you consider one of these features is going to be like more important or relevant than the others. The others are kind of a wash, so just kind of in the noise. But there's times when you need to do average as well. There is a separate thing you can do called global pooling, which is where instead of doing this in tiny little windows and moving them along, and note that we're moving at 2 pixels here, so the stride is 2. And similarly, we're going to have a padding situation as well. People tend to do valid for this kind of thing. Anyway, you can do this on little windows, or you could do it over the entire little image. And this is called global pooling. I mean, it's still a form of max pooling or average pooling or whatever. You might do this if you don't want to do all that flattening. because now I get one number out, or 10 numbers, or whatever the heck it is. And I didn't need to like unroll all these parameters into some god-awful giant array and then do some other computation. I kept everything local, and I'm really only interested at the end then is like, okay, which of my local things is the biggest? And I'm going to call that the winner. Or I'm going to average across all my local things, whatever the answer is. Those are the kind of things that you can do with global pooling. We're going to try that as well. I think I'm going to stick with a flattening for right now, but that's kind of the idea that we can, things that we can implement. Anyway, so we want to do this max pooling. Model.add. We're making great time tonight. Max pool 2D. And let's take a look at it. What do we want? So pool size. Over how many pixels are you going to look at once? This is almost always 2 by 2. Not necessarily, because that sort of cuts your image in half, which is super convenient. We are just going to leave it as that, which means we don't need a stride. I'm fine with valid padding. So again, we're going to lose some size here as well. You might want padding equals same. Again, it will always get the same, in a sense, the same size out. Note that if you have an odd-shaped, an input with an odd number of pixels, and you do max pooling like this, you're going to end up with like 2 pixels hanging off the end that are like going to get ignored or something. So do be cautious about that. Always work with as many powers of 2 of things as you can bear. If you can't do powers of 2, well, just do factors of 2, I guess, is close enough. Anyway, I don't think we need any special arguments here. I think we can just get away with this. We're just going to do max pool 2D. Or rerun this. So now we'll have a smaller model, but we will only have sacrificed those, hopefully, those features that are like least important. And this is on the fly, when the model is run, that you do this maximum calculation. That's what we added into the model here. You don't know ahead of time. Yeah, so now it's 13 by 13 by 2. Ho ho. So now we have only 338 parameters here. We have far fewer parameters than we had before. So, we have added a layer here, but we've reduced the number of parameters, which can happen when you do things like this. Let's run this. 2 epochs, yeah, whatever. This should train much faster as well. It doesn't, it's about the same. Okay, fine. But that is what it is. The gradient computation, I'm sure, is faster, but this is perhaps dominated by the actual computations within the network, sort of the prediction aspect. Accuracy 80% is garbage. That's interesting. Like, this is not getting better. It's not moving hardly at all. Did I mix up max pool 2D here? Did I screw that up? Or is it just, am I throwing away that much information? There's another possibility. Let me check this. Because that seems, well, you know what, let's look at our predictions. Maybe that will inform how bad. In what way is this bad? Yes, so this is always predicting the same bias term for every single thing, isn't it? I do plot. Yeah, do. Cute. Real cute there. That is curious. I did not think that was going to happen. Next pool 2D. Let's see if we screwed something up here. Integer or true pool 2 integers. Factors downscale. We'll have the input. Strides, integer, true pool 2 integers or none. Strides value of none will default to pool size. Valid or same. Case insensitive. Yada yada yada. Data format. A string. One of channels last, channels first. Channels last is what we have. Right, because there's those 2 output channels. The output of the convolution. I don't need an input shade because that's inferred from the previous layer. I don't need an output shade. That is curious. So this model just learned some terrible, terrible things. I'm just surprised it didn't happen before. That's, maybe our learning rate is too high. Let's shrink that a little bit. I doubt that's what the problem is, though. Climbs to about 80%. No, okay, this is moving. It's doing something now. Maybe we got stuck in a bad rut. Maybe the learning rate was too high. These things can happen. But at least it seems to be learning something now, as opposed to nothing. Okay, so that's often a problem you can encounter where your learning rate is set too high. And even though, you know, it's an adaptive optimizer, you're going to have a bad time. If you're stuck in a rut, it's really hard to get out. Better to not get a rut in the first place. So back it up, try some different approach, adjust your learning rate. is a common problem. Hey, these numbers look different. What do you know? Look at the predictions. They look different. Some are big, some are small. That's super good. Could zoom actually help me out here? I'll zoom in on just a few. If I zoom in on a few, a lot. There we go. Okay. Yeah, so you can get some concept of what's going on here. This is probably a little easier. Maybe not. Get some concept that some are large and some are small. And some are kind of medium. Whatever. Are what they are. But is this actually any better? 49. Look at that. That was a significant improvement for this particular metric. The percent of exact matches for all labels in an image. Yes. Yeah. Which of the predictions are greater than 0.5 versus which ones are. So almost half of them. So like if we train this further, this might actually get even better. We're not going to do that though. Yes, the Jacquard index, I'm getting one that's 1, that's super good, and this percent exactly correct. Wow. That is the average there. That's not too shabby. Shouldn't this number be the same as this number? Percent exact matches for all labels in an image. Percent true labels correctly identified. Oh, this is disregarding if I got some of the bad ones correct. Shouldn't this? Yes. Okay. So this number is strictly going to be higher than this metric there. Okay, that's cool. So that's the sort of most straightforward thing. You'll note that we have this like 13 by 13 image now, so doing more max pooling is going to be a pain. So now I'm actually going to take this and change it to padding equals same. I say give me a 28 by 28. I'm going to do this max pooling to get a 2 by 2, and then what we will do is we will add another convolutional layer. Come to D, and we'll compute 2 more things, whatever, who cares. Kernel size equals 3 again, sure. We'll say activation equals rel u again. It's all good. And this is now like a deep neural network kind of thing. Sure, we'll stick with our pattern equals same. Again, just to get the input shape correctly. We'll do that and we'll max pool again. So, what's going to happen? We start with this 28 by 28. You're going to do all this stuff. Do this convolution. You're going to do it 28 by 28 by 2. You're going to do max pooling. You're going to end up with 14 by 14 by 2. You're going to do another set of convolutions. So now we take all those 2 input channels and compute 2 new output things at every pixel position using a window, a 3 by 3 window around it. So it's still 14 by 14 by 2. And then you max pool it again. Now it's 7 by 7 by 2. In fact, let's change this to 3. To 3. Right there. Just so it'll be 14 by 14 by 3 and you'll see the difference. Let's take a look at this then. See if I screwed that up or not. Okay. Always look at the model.summary. Let's see what you're doing. 28, 28, 2, 14, 14, 2. After we max pooled, 14, 14, 3, so we take those 2 input channels, compute 3 output channels on them, whatever they're going to be. This is not necessarily the correct thing to do in any sense. Actually, what we should do, change my mind. What we're going to do is we take 28, 28, 2 is what we're going to compute. Then you knock it down. We went from 1 input channel to 2 input channels, but on half the, well, not half, 1/4 as much data, right? Actually, what I want to do is change this to 4. I want to compute 4 things on the input so that we still have sort of the same number of overall data points. We're not forcing any compression. You'll have 28, 28, 1. You'll compute 4 things in each position. You'll do this max pooling, so you'll have 14 by 14, which is 1/4 the size of the image, but we'll have 4 things in each position instead of 1 thing. And then we'll do the same game. That'll be, the next thing is 1/4 the size of that, but I'm going to have 4 times as many filters. So again, I'll keep the amount of information, the number of parameters will be the same. Let's try that actually. I like that idea. Compile that, model.summary, run that again. Yeah, cool. So again, 28, 28, 4 is what we computed. Knock that down to 14 by 14 by 4. But 14 by 14 by 4 is exactly 784, which is 28 times 28 times 1, which is, 7 times 7 times 16. All the same thing. We're keeping the exact same number of parameters. So we're not losing any information at any step. Or at least our model has the capacity to retain that, just in a different way. I am losing spatial resolution, but I'm gaining more information about each region as a whole, as I crunch this down. The downside being, now my model is bigger on the outside, you know? That's the trade-off. You get to this point, and then it's like, okay, now you have a linear model, and this is the size of whatever that linear model is, plus everything to get from point A to point B here. And this is going to get, you know, a little bit bigger, but yeah, you're shrinking this dimension, growing this dimension. That's the game you gotta play, you know? And it's going to take a little bit longer still, probably. Yeah, you know, I feel like I keep wondering if my GPU is actually working. I feel like this shouldn't even be taking this long. Because there's just not that, well, this has 2 to 16 data points. They are 28 by 28, which is not nothing. I don't know. I think it's still perhaps taking longer than it should. But look at accuracy. Look at the validation accuracy. Bam! 94, according to this. And again, 80% is random. So you're getting something out of this. We won't add regularization today, I suspect, although we have a lot of time left, so maybe we will do that. Bam, and you can probably train this further and get even better. Whatever, that's not the goal. The goal is not actually to build a good model. The goal is to understand what's going on and see, is this a thing that can even be solved? This is why people love deep learning approaches to machine learning. You can just build a model like this, and, you know, in this case, I picked these numbers with some information theory point of view, but often you can just throw numbers in here. Like, yeah, why do I have 2 layers? Why not 3? Why not 4? Why not 1? How large a receptive field do I want kind of question. It's kind of arbitrary, but it works well in this situation. That didn't work. Why did that not work? Uh-oh. Did we lost the signal, didn't we? No, it's just taking its good sweet time. Yeah, okay. That's hosed. Do we still have matplotlib? No. Okay. Matplotlib is dead. Let's just take a look at these predictions. You know, they vary. That's real strong on that particular value. What is validation data? Yes, hang on. Look at our labels, right? VLab, this is the first one. Is this the right number? That's 987, 987, bam. Nailed it. So good at this. Okay, look at our metrics here. 68, even better here. Oh, this percent exactly correct. 68%. Again, in this case, 20% is random guessing. So that's pretty impressive. The Jacquard similarity score is getting pretty good. That's like something you can use. And then the percent of true labels correctly identified, again, getting better. So I bet if you just let this model train for a bit, I'm willing to bet 20 is probably too long. 10. Make it 10 epics total there. Just that it hasn't quite extracted all the information it can. This model has got enough parameters it can probably just learn to solve this. That's actually pretty cool. That you now have a model that's, you know, exactly correct, you know, 68% of the time. Is that as good as a human? I don't know. I had trouble looking at a lot of these and saying, well, what is that? I'm not really sure. But you might end up with something better, something worse. All right, other things you might do. We want to add regularization. We don't need extra layers for that. We can do that in place. I think we can just do that in here. So, regularization. We're on DuckDuckGo. We're going to do some searching. TensorFlow regularization. There we go. Cool. That's great. They have ads. Those are not what I'm looking for. That's not what I'm looking for. There we go. That's what I'm looking for. TF Keras layers activity regularization. That's not super accurate. This is like if you want to add your own custom regularizer right away. That's not really what I need. There's ways to add it built into layers. Oh, there's the average pooling. Global pooling. Oh, that's right. Never mind. We wanted to try the global pooling. Yeah, forget the regularization. That's not important. Has this stopped learning? 95, 96, 96, 96 validation. 96, 96, 96, 96. Yeah, we'll ever finish this epic just for giggles here. Yeah, let's keep. Okay. Yeah, so that model is doing cool things. Run these predictions. We'll just do this top metric here. 73. So that's actually getting decent there. And I suspect you let it train for longer, you could get it essentially perfect. But I want to try something different. I want to try another type of global pool 2D. I think is what it's called. No, what is it called? tf.keras.layers.global pool. Global average pool? Global max pool. Right. Global max pool 2D. Okay. That's what we want. Instead of a flattened. Global max pool 2D. This is probably going to be worse. A worse model, I'm guessing. But this has certain advantages, such that we could pass in arbitrary image sizes all of a sudden. We don't have that situation. But if you're doing this kind of global max, you just say, whatever, I'll just take the max over all of them. I don't care how many there are. Whereas if you're doing a flatten operation, you're computing a specific number of parameters that depends on the image size. And then it means that your layer here depends on the image size. And so your model only works for images of that size. So that's one way that the global pooling can help you get around that. Model.add global max pool 2D. And I bet we don't have to do anything, but this needs to be capitalized. Global. Oh, I didn't actually run that line. Here we go. Global max pool 2D. What does it say? Data format, keyword arcs. Not really that important. Just channels last. That's what we got. Okay, cool. So let's make a new model here. And this will give us one thing. No, what is the output here? And size, number of channels. This will give us 16 things out. So that's actually not terrible. With some receptive field. Let's do that. Okay. Let's do a little bit of training here. Yeah, this is, I mean, it's doing something. Accuracy, well, hang on. This accuracy 80% is random, I said. Yeah, so we're still clawing our way back up to random guessing. We're getting there. Okay, now we're above random guessing. That's as good as we're getting right now. But again, you've chomped down all your information down to the 16 numbers at this point. So you shouldn't be surprised that it's not actually learning, that's having a hard time learning as much, or it's not learning as fast. Before, like we had across the whole image, and to take all those little pieces parts and push them together. Here, I no longer care where those features occur, just that they do occur. And probably we need to, even at like a 7x7 kind of object, you could draw different kinds of images, different digits within there. Particularly when doing two different kinds of digits. That can be tough. So let's do another one of these little modules here. Right, this is a little module. Let's do another one. Except this needs to be 4 times as big as that, so 64. That's probably pretty good. And then we'll max pool again. Oh, that's 7x7 though. Fudge! Yeah, so we're gonna get a slight problem here. Because it's 28 by 28, we only have 2 factors of 2 in that. So I can only chomp down so much. Then we get to 7 by 7, which is prime. So we're going to do padding equals same on this max pool. So one of them will get just padded with zeros, and it'll have to suck it up, and that is what it is. Although actually, now that I think about this, do I even want a max pool? Oh yeah, because this max pooling is irrelevant, right? There's no point in doing a max pool followed by a global max pool. Doesn't make any difference. Because I'm going to compute this thing, and then we're going to compute something else. Okay, here's what we're going to do, though. We're going to do this. I'm going to keep that. And, no, this. I want to try this. I want to see what it does. Okay, let's see how that model did just on this metric. 73, yeah, so you get percent exact matches. Yeah, so 20% there is doing nothing. So 73 is actually comparable to what we were getting after a bunch of training before, so that's actually pretty cool. That's eerily similar, those numbers, actually. What is going on? Percent exact matches for all labels in an image. Why is that the number? That's not right. That makes me super suspicious. What does this predictions look like? They're different numbers. Spread greater than 0.5. Also, here's other stuff. That's super suspicious. Super suspicious here. Okay, I'm very, very suspicious. B lab times this, right? This divided by 2. Oh, no, these aren't. That's just any that we got correct. Is that many? We got 8192 in our validation data set. That's not correct at all. 92. Yeah. Hang on. Updated sum. Axis equals 1, I think. Yes, that is correct. Okay. And I want to know how many 2s do we have in here? And just count me up that. 8192. 8192. 80%. This metric is not what I think it is. This is the number that is exactly correct. I don't know what this is anymore. It's different from this number, though. Which makes me suspicious. Like, why is this 73? Again, random guessing should be 25. If instead of predictions, or 20%, excuse me, that'd be .random of size equals VLab.shape. 24. Really, 25? My math is a little off here. About 20%. I guess you have... No, it's exact matches. Huh. Okay. No. Yeah, just places where we're above 0.5, I guess. Interesting. So 25%. Yeah, I will have to double check my math on that. Anyway. Why is this number, what they're calling the accuracy, different from this number? Which this is the true accuracy. In a sense of, like, if I declare it is that digit, it has a probability greater than 0.5. Has a probability greater than 0.5. Multiply this by this. So only look at the ones where you are. Oh, I see the problem. I see the problem in my little fake metric here. Right. Percent exact matches for all labels in an image. This is correct. This is sort of like what I produced down here. Percent of true labels correctly identified. Because if I get greater than 0.5 on a guy that is a 0, this ignores that. That's why this will be a little bit higher than this. Okay, so this, but why is this still the same number as the other one? That's infuriating. That's exactly the same. I don't know. Maybe I already looked at it. And that was a problem. Anyway, let's rerun this model. It's a mystery, but a mystery we don't have to solve right now. And compile. Take a look at our summary here. I should probably just put that code in the line. Model.summary right here. There we go. So 764, you could, again, max pool this, but you're going to do a global max pool anyway, so don't bother. Save yourself the headache. More parameters. Keep that in mind. So some amount of localization, but we didn't really have this level of localization before. We were really at the 1414 level because we took max pool over all that. But now we have a little bit tighter localization. We got 64 numbers. So, yeah, that's something. how are we doing here? Let's do, we got 10 minutes left. Yeah, it's taking longer to train now too, 20 to 30 seconds. Okay, accuracy is climbing fairly quickly though. We're not going to let it finish all these epics. Probably going to let it finish 2. I just change this to 2 so I don't lie here. Oh, that's real good. And again, this is accuracy like updated per batch. When you get to the end, you get the validation accuracy, and that a little bit better. But again, 80% is random guessing. I think we got up to like 95, 96 when we let it train for a little bit. Some of the other models. We'll see if this gets that high, and maybe after the stream, I'll just let it go. You'll see what happens. Come on, go baby, go. 94, not too shabby. Okay. Run our predictions. They are different, right? They are different. It's the correct value, but that's not so huge, right? It's not like 0.99999, whatever. Only 61. So that's currently worse than the previous iteration, but it didn't get to train for as long. These other kinds of things. You got all these other numbers you can compute. All kinds of cool stuff. So, I don't know, I kind of want like one more. Just give me one more of these, right? Just one more layer. That'll solve all my problems in this network. Clearly. That'll be the answer. 64 times 4 is 256. That's what I want. We'll do the max pool again. So this is getting kind of deep now. You might have problems with your gradient. You're not getting a lot of information going back to your early layers. This can cause trouble. Let's do this. Yeah, no, now it's taking like 40 seconds. A little bit longer and longer. But, and here, I actually am screwing around with the level of information I have. I've got a large number of parameters here. But, then I do this global max pooling, and it's not insane going from here to my dense layers. I'm just making my life complicated here by trying to keep the same amount of information available. So what's that going? 93%? That's not bad. Not for one epic, no. Not bad at all. 95? Again, it takes more time, because you have more parameters. Hopefully this is better capturing sort of global scale features, and I decide by the time I've gotten to a 4x4 resolution, it doesn't really matter where things occur in the image. But again, your image will have to be big enough to do this many convolutions. If your image is only 8x8 to begin with, you're going to have a bad time. But you could handle much larger images, keeping in mind you're only looking over a certain receptive field. And it's like you're looking for a small thing in a large image, then this global max pooling is exactly what you want. And that's not too bad. 96% there. Make our predictions. Look at the SK learn. Oh, that's taking some time. 72. So comparable to some of the other things, but not whatever that spooky maximum value is. Okay, I think that is sufficiently interesting. We have a convolutional model that does something. Hey, awesome. We tried to preserve the amount of information that we have. We didn't futz around with the activation that much. We could have. There's things you can do there. We tried both the flatten type of model, where you unroll everything in the convolution, so you keep all the different pieces of spatial part, but you throw away the real spatial information. We also tried the global max pool, which I haven't done before, so I was glad that worked out. Where you're just looking for the sort of the biggest thing in each channel. You don't go where in the image it occurs. It's ideal if you're looking for smaller things in a big image. That might be kind of relevant. That gives me an idea, actually. I might look harder at that. But that is a way to get a single piece of information out from an arbitrary image size. So that can be really valuable if that's what you want to do. I'm not sure what we're going to do. Next week we might try to make a model that looks like, has a similar architecture to standard outside models. Or we might try to make a model that's somehow informed by the data, but not by this data, just like what the digits look like. Something like that. This is actually pretty good. This is better than the total garbage we were getting before, because we shouldn't be surprised by that, because these little convolutions, they capture little itty-bitty features. Like one of these channels might be finding tiny little edges, one of them might be finding tiny little corners. You build up a bunch of edges and corners, you can start to make more complex shapes. You make those complex shapes together, you start to make things that look like digits. Hey, what do you know? And then you can predict oh, what 2 digits look like they're most in here. Even though you slap all these things on top of each other, it's like, well, this part looks a lot like a 2, this other part looks a lot like a 7. That's enough information for your network to determine, aha, that's exactly what's there. Except the network never says, aha. The network just looks at, all right, for this batch, this bunch of stuff was wrong. The right way to go is that way. That's towards the correct answer by a little linear interpolation. And you update everything that way, and you redo the process, and you update it that way. There's no aha in the model. I want to make that clear. That's aha is apparently only for humans. If we can get to that with a machine, that'd be great. But this is still called dopey for a reason. Oh well, that is all I have for tonight. So thanks everyone for watching. This will be uploaded to YouTube shortly. And we should be back again next week. Stay safe in the data mines.